Okay, folks, welcome back. Run Middle is on air again. So last week we didn't have our usual show because I was on Systems Distributed, the conference in Amsterdam, which was really cool. So if you missed on that, please consider booking the tickets for Systems Distributed 2026 beforehand. But I'm finally back, and today we are going back to discussing Deterministic, this exciting database which is implemented in Zik, which assumes that the disk can fail, which follows this super weird tag style, which doesn't have dependencies, and which doesn't even have a database schema defined by the user, and just hard codes, double entry, bookkeeping. So, what? It seems screen is dark. Well, there are some complaints in the Twitch that something is not working, but I have Twitch opened, and I definitely see myself in Twitch. So probably it is someone's Wayland problem. Okay, so where we are at. We've been discussing simulator. Let me find the simulator. Okay, so this is the simulator. And okay, so window management on this operating system isn't really great. Likely you aren't able to see it. Okay, so again, overview of the simulator. Like Tagevital as a whole is a distributed system containing many nodes. But when we are running our tests, we are running them in a simulator, which models all of the nodes and all of the clients on a single thread. And the overall idea behind the simulator is that we throw random events at our simulated cluster and then check that it doesn't fail. The devil in details, specifically, how exactly are we generating these events? And this is something we've been looking at last time. So let's continue with that thing. As a reminder, we have workload, and we have auditor. So the goal of the workload is to generate events, and the goal of the auditor is to check that the behavior of the system is correct given the events that we've generated. So I think last time we mostly covered workload, but haven't really mostly covered workload, but haven't really touched the audit. And today we'll go into cover this gap. But because that was some time ago, let's quickly walk through the auditor. So we have this build transfer, well, not auditor, workload. Build create transfers, which is kind of like, a core function. It takes an output parameter, transfers. So you see, this is not const. This is not const. This is an output thing. And we initialize this thing with a transfer. And transfer follows specific transfer plan. Okay. People still complain that the stream is broken. But, well, I mean, it doesn't seem broken to me because I definitely see myself on Twitch. So that should be fine. Let me also check if I can hear myself on Twitch, because maybe it's audio that is broken. Boa tarde. Okay, do I have audio here? Boa tarde. Okay, no, even the audio is fine. So, folks, I assume that the stream is actually working, because it definitely, like, the Twitch thing definitely works on my side. So perhaps something is broken in Twitch and it doesn't successfully transfer the stream to your device. But yeah, hopefully it isn't. It is broken. Okay, yeah, okay, yeah, sorry. That is Twitch problem. Luckily, I am recording this as usual. So even if you aren't able to see it live, there will be a recording on YouTube relatively soon. Sorry for platform issues. Okay, so build create transfers. So basically, we create a transfer and we create a transfer which follows a plan, like whether the transfer should be valid or not, whether we expect the transfer to hit limit, whether we expect transfer to be single phase or pending posting, whatever. So let's quickly see how this all fits together. So how do we use the results of the build create transfer? So we use this in build request batch. Build request batch is a part of build request. And build request is called by the simulator to create a request. So now let's see like the flow of the reply. What are we going to do with the reply? So okay, first we create a request, then we do a request, and presumably on Okay, so we have like on cluster reply, on client reply, and those are hooks. Okay, let's see. Let's see what are we doing. Okay, so this is on cluster reply. So I think this is generated from inside the replica. Do we have event? Okay, so yeah, presumably this is where we generate a reply. Okay, so we have a reply sequence. Which contains pending reply, which are ordered by op, pick. Okay, so on cluster reply, we insert this reply into the reply sequence. And while the reply sequence is not empty, we get the next op. And while we have the op, we verify that, okay, this is indeed the reply to the prepare we are expecting. And then we call workload on reply. So before, okay, so let's make a note here. Note here. Okay. But let's see what are we doing in client reply, just to understand like the overall flow. Okay, here we just counted the replies delivered to the client. So this is not interesting, and presumably everything that is of note is going to be in this on reply. Okay, multi-batch. Okay, do we have multi-batching? Okay. Oh dear, so many things to still cover. This is horrible. Okay. This is, I think, the thing. So yeah, okay. So we call auditor methods like auditor on create accounts, auditor on create transfers. So okay, let's jump into the auditor on create accounts and on create transfers. I guess okay. Ow. Oh. My back. My back still hurts after all this traveling conferences. But no worry, let's continue. Okay, so what does the auditor do when we create accounts? Well, before figuring out what the auditor does, let's see like what the auditor is. And okay, I kind of like, okay, we really should change this. Like, I really hate when the extracts start with types, because I don't want to see the types. I want to see the types, but not as the first thing. As the first thing, I actually want to see the fields. So this layout is like much better, and we should, I think, add it to tiger style and fix all our types. But never mind. Okay, so we have PRNG options, timestamp, accounts, account state, query intersections. So yeah, so I believe query intersections is kind of like that thing where Jepson found the bug. In that let's see, that I think our problem was that we kind of like generated query intersections in the beginning, and we are doing interesting ones. Oh, I guess, okay, let's ignore query intersections for now, and okay, maybe let's do this. Queries, including whopper. Let's just review queries once we get to like queries. Okay, pending transfers, pending expiries, in-flight. Okay, seems relatively straightforward. What you would expect to see in the state. So basically, we kind of like build an in-memory model of everything that Tagebital stores durably and replicated. Okay, so take in-flight. I wonder. So, okay. The first thing we do is that we get an expected result from the set of in-flight results. So I am curious where we add something to in-flight. Get output, expect create accounts, and presumably, okay, yeah, so when we create an account, we set what we expect in the create class. And this is, again, this I think is not the way to write these kinds of checks, because, like, you know, if you need to predict the result of your operation before you execute it, that severely constrains you in what kind of operations you can execute. And that means you might not cover, like, you know, everything. So a better strategy, I think, usually is to run just arbitrarily random operations, and then after the fact somehow verify that the result that you got is correct instead of trying to predict it from the start. Okay, so we take this expected result and we check that it actually contains the expected result. Okay, now if the result is correct, we say that, hey, the account is created with the current state, with the current timestamp. Why account timestamp? Oh, okay, yeah. With timestamp, blah 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 blah. Okay, so that seems relatively simple. Okay, on create transfers. What do we do on create transfers? Well, the same thing. We check that the result is expected. Query intersections we are ignoring. And then, okay, so this is like pending posted. We'll maybe cover this separately. Actually, have we covered pulses? Pending. We haven't covered pulses. Okay, this is pulses pending posted. Okay. So let's see like the usual case of single phase transfer. Okay, so if it is successful, and that means that it is not like a link transfer which failed, we go and we okay, if this is pending, we are not interested in pending. Okay, we go and we modify debits and credits. And I get, but you actually don't check the result. So I guess we check the results in all lookup accounts. Where we go and check, that they are bytewise identical. Oh dear. Now I'm kind of like feeling super bad because I was late by 10 minutes, for which I apologize just a little bit because, well, I mean, I'm still recovering from a conference, so I'm not super online. Let me put it that way. But also, I kind of like expected that we'll have to cover a lot of ground today, but I think that's actually basically it. I mean, like, you know, auditor maintains a set of accounts, and like, really, like, this this is all, like, you know, debits posted plus equals amounts, credits posted plus equals amount. Like, this is the whole payment table does. It really is that simple. Like, you know, it's just like the two lines. Like, and like all the complexity is actually in making this fast, available in the face of node failures, correct and durable in the face of disk failures and all that stuff. Okay, is it really all there is to do? There is to auditor. Wow, it feels okay. It feels like it. I mean, why is it so simple? Like when I was reading this code the first time, it was kind of like super horrible and complicated. But yeah, it feels like it is just fine. Okay, so what are we going to do next? Because I think we kind of like covered everything there is to Whopper, really. I mean, it is done. Okay. There's been a change of plans. Let's look at our unit tests. So okay, Whopper is done. To recap, Whopper simulates a whole cluster on a single thread by submitting random events into this cluster, random requests, and then checking that the results are as we expect them to be. Now, the problem with Whopper is that it is very good at finding bugs, but it is pretty horrible for debugging, because the failure you get, even if you minimize it, is typically pretty large. For debugging and for, like, you know, otherwise like double checking that things work as expected, we do have some handwritten tests. So let's find some Okay, so let's find some simple test and let's look how it works. And it actually like uses the same underlying infrastructure as a Whopper. It's just that the test is running manually instead of generating random things. And okay, this is the test. Partition flexible quorums. We have partition where a cluster of 4 is split into 2 halves. And the half that is the primary should be able to continue. So we initialize our test context, and then we create clients. We run the cluster so that it does the initial view change so that we get a primary. And then we do a partition. We do the partition by stopping backups 2 and 3, and then run for some more time. And then we do requests. And we expect things to continue working. So, like, very easy, very simple. And there is 2 lessons here. Lesson number 1. Lesson number 1 is, although you do want to rely on randomized testing, it is still useful to have some amount of handwritten tests. Lesson number 2. When you handwrite your tests, you should never ever call internal APIs. All the tests should call only the APIs exposed by a domain-specific test framework. So you see, like the actual code is replica, but we don't interact with replica directly. We have this test context. And when we, want to make a request, we don't just go to like the client and make a request manually. No, we ask our test context to make a request. When we want to stop a replica, we don't go to a specific replica and initialize it. No, we ask the test context to go and stop a replica. The smaller win here is that our test is just concise. You see, it is really like quite readable. The bigger win, though, is that this way our tests do not freeze the code. So let's say I change something about my replica. Like, I don't know, let's say I add graceful shutdown. I haven't read the crash-only software paper. I don't know that databases should never ever have graceful shutdown. I decided, okay, it's a good idea to add graceful shutdown to the replica. That means that the API I need to call to stop the replica change. And were I to use this API in my test directly, I would have to update this test. Moreover, just let's see how many calls to stop we have. Okay, we have 47 instances where we stop a replica. So if I were to change the API of my replica, I would have to upgrade 47 tests. And that is like, hugely discouraging, because that means that I wouldn't be able to rely on my tests during refactor. I did a refactor, now I want to run the tests, but now the tests don't compile because there are like 47 or like 147 usages of the API that I'm refactoring. So to like do this refactor, I would have to refactor the tests, and that significantly increases the activation energy to do the refactor. And this also significantly increases the chance that I mess up during refactoring the tests. That's that, like, I do a refactor, and then simultaneously I change the tests, and I accidentally modify the test. So now it passes by accident, and I didn't notice it because I did two things. Okay, so question in comments. How can I convince my team to follow this through? I see patterns of it's easier to call some private API to set up the state, check the state in many places, but I can't find concise and convincing enough argument not to do that. Well, concise is the keyword here. So I actually have an absolutely massive blog post about testing, because I do see that, like, like people generally don't understand how to test. There is a lot of information about writing tests, but it is like, well, I mean, it is not misinformation, because it isn't, like, deliberately misleading mostly, but it's really just like, some like mythology. Like, like before we had science, we kind of like ascribed various natural phenomena to like gods or spirits or whatever, and we had like a whole huge corpus of literature explaining the world without any connection to reality. So I kind of like feel that the testing discourse is like in the same place, and while there are explanations of like how to test, they really aren't readily available. And in general, it is like huge battle to change the projects. So what would be my practical advice here? Well, first of all, like, go and read everything there on testing. Not only the stuff that I recommend, but also the stuff that I don't recommend. Like, go read about mocks, go read about behavior-driven development, go read about all the bad takes about TDD. Because, well, if you want to make your point, you need to understand the arguments of the opposite side very well. Then, yeah, the best possible way to set the project culture is to do it from the beginning. Like, if you start a project, then make sure that the first 10 tests are correct from this perspective of like how you do testing. Then, because most of the tests, okay, so I think I'm running low on my battery for microphone. So let me quickly check if I can recharge myself without tying me too close to the source of power. Okay, just a moment here. One, two, three, 1, 2, 3. I'm still not dead. Okay, now I'm charging and you could still hear me, and I can even move to some degree. Perfect. Okay, so the next big thing is like you start the project with good tests, because this is the iron law of tests, like the induction axiom of tests. Test number n+1 gets written by taking test number n, copying it over, and slightly modifying. So if you start with good patterns, the good patterns will continue. If you start with bad patterns, the bad patterns will continue. But again, this only works if you have a lot of leverage at the beginning of the project. Now, suppose you are working on like brownfield projects and the tests are not good. What are you going to do? Well, I mean, honestly, here I would probably recommend just considering continuing the existing pattern and not applying drastic changes, and instead like trying to do tactical improvements, or at least not applying drastic changes from the beginning. If you join a brownfield project and you don't like the tests, please hold the urge to go and rewrite everything. You probably are right that the tests are not good, but if you try to rewrite them immediately after joining the project, you will likely fail for two reasons. First of all, you actually need to accumulate social capital. You need to, convince your colleagues that you actually know what you are doing by doing good work. You need to build trust. And second, although tests might be genuinely horrible, probably there is at least some amount of wisdom accumulated there. Probably there are some reasons why tests look that way. So it is important to internalize that before you embark on refactoring. And you can't usually find those things by just reading the code. You really need to try to implement a couple of features in the project and do that. So, okay. Now, assume that you've been with a project for some time, you have some amount of social capital, and you kind of understand that, test suite is horrible. There are some good reasons why it looks that way, but actually it could be better. Well, the next step is probably to talk with the person who has the most social capital in the project. It might be the manager, it might be team lead, it might be some IC with high level of trust. And there, your goal isn't really to, your goal is of course to convince them that your ideas are brilliant and you should go and refactor this. But actually, not really. The goal is really uncover information. You really should look together at this problem and figure out whether it is a mistake or it is not a mistake. If you successfully convince the person that this is indeed a mistake, well, because that person also has a lot of social capital, together you actually could say, okay, so from this point on, we going to write tests in a better way. If you aren't able to convince them, then well, it's you shouldn't try to fight adversarially with your colleagues. It's never going to end well. So in this case, okay, so just continue business as usual. If you genuinely believe that they're making a huge mistake and don't value your arguments, well, at this point, please reflect. Maybe you are wrong. It's super, when people disagree, it almost always is the case that the truth is somewhere in the middle, not exactly in the middle, reverse stupidity is not intelligence. You cannot find the truth by just looking at the perfect center of everything that people say on the internet. But usually the truth is somewhere between the extreme opinions. So yeah, okay, reflect. If you still kind of convinced that they are all wrong and you are right, well, maybe time to find a new team. That's normal. And again, and even in this case, it doesn't necessarily mean that the team is objectively wrong. There is such thing as taste. There is such thing as context. It just might be the case that there isn't a good match between the team and you, and it doesn't mean that either of you are wrong. You are just different. So okay, assuming that you've been a while with the product, you understand everything, you see all the complexities, but you also see how you could make this easier, and you have buy-in from people who have actual formal or informal say in the project. How do you approach this thing? I'd probably do this. First, because there is induction law over tests, that the tests are going to be copy-pasted, I would really invest a lot of time into just spiking this. Spend a whole week working very hard on refactoring as many tests to the new pattern as possible. For two reasons. First of all, to actually double check that your new pattern is better. And second, to actually convert the bulk of the tests. Because after you have converted the bulk of the tests, like it will become much easier because people will be like copy pasting good stuff. So like you need to go like beyond 50%, or at least like, beyond 50% in a particular subsystem or something like that. Okay, so if after that you are convinced that, hey, new tests are good, then you merge them, like that pull request. And after that, you should start subscribing to every single pull request. And you should start looking at every single request that touches tests and actively educate your colleagues about new way of writing tests. So if you see that someone is trying to resurrect the old way of writing tests, you say, no, this is how we do this. And well, you are on the hook for that until the entire test suite is rewritten. But generally, I think it is like generally like a good idea to push for that, provided that you convinced yourself and enough of other people that this is a good idea. Okay, hopefully this answers the question. But let me like circle to the beginning. The easiest way is just to do this right from the beginning, or to join the team which does this right from the beginning. Like it's like you don't have to fight every battle. Like better find like-minded people. Okay, next question at Twitch. I'm really grateful for the questions here, because yeah, I've kind of like messed up this episode on so many levels, and you are like saving my bacon here. Do you think programming languages change the way you approach a test? Like, would you use a different test paradigm if the language tries the garbage collected, etc.? Great question. So, my answer here to whether programming language matters for testing patterns is yes and no. In that sense, I think the actual testing patterns are the same across the language, and the testing pattern depends on the project and not on the language. That being said, some languages make expressing certain patterns easier and certain patterns harder, and they actually might help you to see how to write testable code. As an example, let's take Rust. So, Rust versus Python and JavaScript. The problem with Python and JavaScript is that those languages are highly dynamic, and that is very easy to mock the code. There is very little friction to mocking the code. So you kind of like might be pushed towards like, just mocking everything. If you look at Rust, while mocking is possible, there is a lot of friction. Mocking code is possible. There is a lot of friction to doing that. And like, while you might try to apply a lot of mocks in Rust, like, you will have plenty of time while you're fighting the borrow checker and waiting for compiler to compile your pile of proc macros and traits, which allow for mocking, to think about whether like mocking might be a good idea or not. And in particular, like, Rust really convinced me of this specific thing about the tests, that let's actually write this down. Mock IO, not code. Zoom in, zoom in, zoom in, zoom in. Yeah, really, like, don't mock code. Mock input output. So, like, you see, like, that is the thing. Like, your system communicates with outside world. You want to mock the bytes that go into your system and the bytes that go out of your system. And it kind of like doesn't matter how that thing is expressed in code. You never want to mock a class, a function, whatever. You might want to mock a functionality. Yes, it is obviously going to be expressed in as a class, and you might want to use polymorphism to do that, or maybe even like, actual dynamic mocking library. But the insight there is that, hey, what you're mocking is like the physical thing and not your code. And this is an insight which is easier to see in Rust because Rust makes it harder to apply to just directly mock the code. Okay, so let's see. Do we have some other interesting tests? Yeah, let's find something not too horrible. Okay, this is all very, very hard. Okay, yeah, this is this one is interesting to see. So this test tests state sync. Normally, when a replica is just a little bit behind the cluster, it requests missing prepares and then just executes them normally. If a replica is far from the cluster, it might not recover by requesting prepares, because prepares might be evicted from ring buffer log of other replicas, and it needs to state the sync. So what this test shows is that actually replica might not be that far behind the cluster to trigger state sync. And let's see how we do this. Okay, so we start with 3 replicas. We commit up to the checkpoint. Then we isolate backup 2. So we don't crash it. It is still running, but there is no network connection. Then we require everyone else to process up to the trigger. And then we corrupt the latest preparer in the checkpoint. So this is fine. So this preparer is now corrupted. But these replicas are on the checkpoint, which already includes this preparer. So they don't actually need this preparer in the log. And now we actually so this one is not necessary. Doesn't feel like it is super necessary, but well, okay. We kind of like commit a bit more. Well, I guess this is nice to see that this preparer is no longer needed. Okay, now we say, okay, let's unpartition B2. B2 now can participate in the cluster. So B2 is behind. So B2 is still on the checkpoint 1 minus 1. And this is just a constant, which is like, is some like op number. Okay, do I have... Okay, no. So B1 is still at checkpoint 1 minus 1, but everyone else is... so B2 is just before the checkpoint 1. Everything else is past checkpoint 1, and they don't have the op for checkpoint itself, so B2 cannot prepare. It has to state sync. So we check that we can commit further and check that all replicas are at the same at that latest op to which we committed, including B2. And you see here is another nice meta pattern that often you want to be jQuery, really, because the magic of jQuery is that it always operates on collection of DOM elements. There is no in jQuery, there is no jQuery API to pick all a single element. It is always a collection of elements, and this turns out to be more useful paradigm most of the time. So in our testing domain-specific language, this test context.replica returns a collection of replicas. So if you pass A0 here, it will return a single replica, which is a primary. If you pass B1, it will return you a collection of a single replica, which is going to be the backup, which is next to the primary in the topology. But you could also pass wildcard. You could say, okay, I want all replicas. And then you could check that, hey, all replicas actually do agree on commit. Okay, so that is the test in DSL. Let's see how the test context work. Well, you see how the test context work. The main thing in the test context is this cluster, which is the same cluster which powers our Whopper. So this the same cluster is what we use for unit tests. And really, there isn't anything super interesting in this test context otherwise. So I don't know. Let's see. Request. How we do request? Well, we go for the clients in this text context. We send messages until we send how many messages we wanted to send. And that's basically it. There isn't any super fancy, tricky things here. It is a bunch of unpleasant code to wire up all the APIs, but this is the key. This wiring up code is written once, and all the tests are executed against this DSL, and all the tests are isolated from changes in the underlying API. Okay, I guess let's call it a day. This is slightly less than an hour, but well, again, I'm still recovering from the conference, so I would allow myself to cut this one short. Hopefully this was interesting. Hopefully you learned a couple more things about the testing, and I think we could congratulate ourselves with finishing yet another arc of our Tagemittal story. We now understand how to build deterministic simulation testing, and also just unit testing reusing the same infrastructure. So next time we are going to pick something from this list, as we have somewhat active chat today. So chat, do you have any suggestions for a specific topic out of this list to cover next? Or maybe you could suggest your topic, which is not in this list at all. And no worries if you don't do this. We could, I could always pick something myself. Performance mode, Performance mode. Okay. Thank you. No, I am not sure how this nick is pronounced, but we are going to talk about performance mode next, which actually means that I've just lied to you, because performance mode is also part of our Whopper infrastructure, which we use to deterministically check algorithm performance. Okay, so let's see each other again at 5 p.m. UTC live on Twitch, which is going to be in 22 hours 55 minutes from this very moment. And if we fail to meet, then you could always watch recording on YouTube. Well, you could always watch recording on YouTube. I sadly cannot just miss a stream and still have this recording manually appear on YouTube. Like our artificial intelligence is not that good, likely for me. But anyway, let's stop rambling and meet again next week. Thanks for watching and goodbye.